So today we're going to look at linear equations. Linear equations all have the same sort of format. I've written down two examples here that we're going to look at first and how to graph them. And then we're going to generalize some important things about them. The first one here is y equals to 3x plus 5. The second one here is y equals to negative 4x plus 1. These two are both in the same sort of format, but there are other formats that we will be looking at as well, but the idea behind it and how to find points in the line works regardless of what format it's in. So if we're going to use the first one here, I'm going to look at creating a table of values for just the first equation. Now, I would suggest that you use positive and negative values, just so you get a good idea of the shape of this graph. So let's just start with, say, negative 2. Now, how you figure out what the y value will be is that you use the equation, and wherever you see an x, you replace it with negative 2. So, for instance, in this case, y equals 3 times negative 2 plus 5, which will then give me negative 6 plus 5. Negative 6 plus 5 will give me then negative 1. So that would be our first coordinate pair. On your graph then, at negative 2, negative 1, we then plot a point. Now if we continue on with the same idea, let's say I start moving towards a positive. Let's say I use negative 1. Wherever I see an x, I replace it with negative 1. I evaluate it out, and I see that I end up with 2. So at negative 1, I have a point here at 2. If I do the same thing for the next number, which will be 0, 3 times 0 is 0 plus 5 will give me then 5. And if I keep going, 0, 5, and I plug in 1, 3 times 1 plus 5 will then give me 8. Now, you should start to see these are all linear equations, so the points when you start to graph them should start to form a line. So you should be able to connect these after you've done 3 or 4 to actually see that they are in fact making a line. A couple of things when you are drawing your lines, try to keep them as straight as you can when you're doing freehand. Make sure you include arrows at the end because they do go on. You could technically plug in any x value to continue on this pattern. So that'll be our first one. Now we're going to look at the second example here. I'll do it in green so it's a little bit different. And again, we can choose any x values you want. So, I don't know, let's plug in negative 2 again. Let's see what happens. So in this case, for my y is going to equal negative 4 times by negative 2 plus 1. If I go negative 4 times 2, it becomes a positive 8 plus 1, so then I get 9. So at negative 2, I have a point up here at 9. If I do the same idea, but this time I plug in negative 1. Now I get 4 plus 1, which will give me 5. So at negative 1, I will have a point here at 5. If I plug in 0, I get 0 plus 1, so I get just 1. And if I plug in, let's say 1, for negative 4 plus 1, you're going to get negative 3. And I could do another one if I wanted to, so let's say I plug in 2, negative 8 plus 1, so negative 7. And again, I'm getting the pattern that looks like a straight line. Connect it the best that you can. I'm not using a ruler, you probably won't be either, but make it look as straight as you can. And there you go. Now those are some nice integer value points, but there are a couple of things I do want to point out. And you can take a look at these as well. When I had a positive value in front, it went from quadrant 3, up to quadrant 1. When I had a negative value in front, it goes from quadrant 2 down to 4. It's one nice little thing that we've got in terms of determining which quadrants it's going to go from and to. Something referred to as slope. The 3 and the negative 4 are something that we're going to come back to and talk about in terms of slope. Now there is a nice little thing as well that you can notice on here. This last number here, 5, when I plugged in 0 for x, you get the 5 because it cancels out that x term. Same thing here, I plug in a 0, I get a 1. This coordinate is where it hits the y-axis. It's when your x value is 0. These are both referred to as y-intercepts. So sometimes when you're given an equation of a line in this format, you can determine automatically just by the sign of the slope which direction it's going to be going and where it's going to hit the y-axis. So your y-intercept and what's referred to as our slope are going to become very useful when we're doing these problems. Now these are all examples of more lines. They're in a different sort of format than what the other two examples were that we just looked at. Now some of the key things to know whether or not these are lines or not depend on the degree of the variables. Ultimately, we will always have a y to a power of 1 and an x to a power of 1. All linear functions do not have exponents on our variables besides 1. Now, this one in the middle here is in a format similar to the ones that we looked at because y is isolated. From this, it's very similar. If I plug in a 0 for x, I'm going to get negative 2 as a result for my y-intercept. So I can read my y-intercept nicely from this equation. I can also use a table of values and plug values in to figure out other points. What's a little different here is now we have a fraction in front. It just means that now that you have to actually work with fractions and do your evaluations. Do not round up. Make sure that you're using fractions throughout everything. When you're graphing a fractional amount, you're estimating an approximate decimal value for it. This one here, at the first one, we can't necessarily read things off of this directly as to the shape and the direction of where it's going and where the y-intercept is, but I can still plug in a value for x and solve for y. I can also manipulate the equation and isolate for y beforehand. In this case here, 2x plus y equals to 4, I could technically isolate for y. Technically it's being added by 2x on this side, so in order to move 2x to the other side, minus 2x on this side, minus 2x on this side, I now have positive y by itself, minus 2x, plus 4. So now, it's in a similar format to the last ones that we just saw. I can plug in 0 and get my y-intercept, and I can plug in other points to see some more points on the graph. I can also see that it's a negative coefficient, which means that I'm looking at a slope that is a negative slope going from quadrant 2 to quadrant 4. The last example here is also linear, but we can again isolate for y if you'd like to put it into a format similar to the middle one, or just plug in values for x and solve for y each time. If you wanted to isolate for y, you have to use your distribution. So 2 times everything inside the bracket to distribute this out. You get 2x minus 2. To isolate for y, I need to add 5 to both sides of the equation to get 5 to the other side. Then you get y is equal to 2x plus 3, negative 2 plus 5. So now it's in a similar format again. I can plug in 0 here to find that my y-intercept is 3, and I have a positive slope, which means it's going from quadrant 3 to 1. Now it's isolated, so it's a little bit easier to work with, but you don't have to isolate it in order to work with the table of values. If I was to work with this first example here, and when I wanted to make a table of values, and let's say I just wanted to use a value of x equals to 1. wherever I see an x, you replace it with 1, and then you can solve it. Now I've got 2 plus y is equal to 4. How do you isolate for y? You minus 2, so then you get y is equal to 2. If I wanted to use the equation that I've already isolated for, it would do the same thing. Y is equal to negative 2, replace the x with the 1, plus 4. Then y is equal to negative 2 plus 4, which is then y is equal to 2. Same thing. So whether you use the original format or the isolated format, they'll do the same thing. You're just replacing the x term with the value, and then you're creating your table of values. So that way you can then plot it on a graph. So at 1, 2, I have a point. Now working with fractions is a similar idea. Now this one's already isolated, but there is a little, I guess a little bit of a trick. You're looking at how to work with this and not have to work with fractions. Most of you prefer not to work with fractions. So instead of just choosing x's randomly, if you use multiples of the denominator, it helps to cancel out the denominator. What I mean by that is if I choose, say, x to be 3, my denominator is 3, and I'm going to replace wherever I see an x with 3. Now remember, when you're working with fractions, that's the same thing as saying 2 over 3 times by 3 over 1. Numerator multiplies with numerator, denominator multiplies with denominator, and we can also cross reduce. So then, as a result, we get 2 minus 2, so we get 0. Now if I was to use a different value in here, let's say I use something that was not a multiple of 3, if I was using something that was not a multiple of 3, you're going to end up with 4 over 3 minus 2. You'd have to find a common denominator, which is totally fine. You can do this. 6 over 3. So then we'd have negative 2 over 3. So if I did decide to use 2, I would get this, but it's just not as easy to plot. Whereas if I use another multiple of 3, let's say I use 6. 2 over 3 times by 6, remember that's the same as 6 over 1, we would be able to cross reduce 6 and 3, and I'm left with 2. 2 times 2 is 4. 4 minus 2 then gives me 2. So then I don't have to worry about my fractions. I get a nice number, and I can still plot it on a graph. So by using multiples of the denominator, it helps us find integer values and not have to worry about estimating our fractions when we're graphing it on a grid. Now in this case here, again, if I wanted to do my table of values, I can do it with either the original format that they give me in the line or my isolated format. Let's just say again that I want to use, I'll say x is equal to 2. If I use the original format, y minus 5 equals 2 times, and I replace an x with 2 minus 1. I would then go through all my work and say, well, 2 inside the bracket, 2 minus 1 is 1. Y minus 5 is equal to 2, 2 times 1. I need to isolate for y, so I add 5 to both sides. I then get 7. If I use the other format, y equals 2 times 2 plus 3. 2 times 2 is 4 plus 3, it's 7. So either way I get the same thing. It's just what you're more comfortable with. If you prefer to isolate first or use the original, either way you'll get the same answer.